Hi, this is Math 2231 remote delivery for April 27th, 2020, and this is part 2 of the area between curves. You know what to do and when to do it, so take advantage of that to make your learning as rich. Again, reminding you of the process, it is really important that you sketch a graph. In fact, you probably don't get anything done until you sketch the graph. And I want to note here that often this involves, in addition to algebra, it requires you use some calculus that you learned from the first part of this course, thinking about what are the maxes and mins and where's the graph concave up and concave down, increasing and decreasing, and so on and so forth. So getting a good sketch is critical. You use the sketch and algebra to find the limits. What are the limits of the integrals? And then you have to set up the integrand. So you're finding the limits and setting up the appropriate integrals to represent the area that you're trying to find. Last but not least, and very importantly, compute the definite integrals. You really have to do all three of these. So let's move on to a problem involving trigonometry. Determine the area of the region enclosed by y equals sine x, y equal cosine x, the vertical line x equal pi over 2, and the y-axis. You know what to do and when to do it. Let's see how you did. So, the vertical line x equal pi over 2 is over here. The y-axis is also known as x equal to 0. This is the graph of y equal cosine x. This is the graph of y equal sine x. What we're seeking to do is we're trying to find the green area, and we can solve the curve by setting sine x equal to cosine x and doing algebra, or perhaps just from our knowledge of trig, but we have to know that those two things intersect at pi over 4. So the area is going to be the integral from 0 to pi over 4. The cosine is on top, minus the sine, plus the integral from pi over 4 to pi over 2, and now the sine is on top and the cosine is on the bottom. So then we do these integrals. The antiderivative of the cosine is the sine. The antiderivative of the minus sine of x is the cosine of x. And by the fundamental theorem of calculus, I'm going to be evaluating this at 0 and pi over 4. Do pi over 4 and then minus and evaluate it at 0. The antiderivative of the sine is going to be the minus cosine, and the antiderivative of the minus cosine is going to be the minus sine. And these are evaluated at pi over 4 and pi over 2. You do it at pi over 2 first and subtract the value at pi over 4 from the fundamental theorem of calculus. If you substitute those numbers in, and you get this. Remember, we do these without calculators in our next two assessments. Let's do another problem. Here we're to determine the area of the region bounded by it is y equal x e to the, and that is e to the minus, that is x squared. It doesn't show up very well, but it is minus x squared. This is the line y equal x plus 1. That is the vertical line x equal 2, and again, the y-axis. You know what to do and when to do it. Let's see how you did. So this is the graph of y equal x plus 1. It has an intercept of 1 and a slope of 1, so that is the graph. This curve, and you might remember this from L'Hopital's rule, this goes to 0 very fast because this exponential curve dominates that. You could prove this using L'Hopital's rule. You also could use your calculus to figure out that the maximum of this is way less than 1, and so this blue curve actually is always on the top, and the red curve is always on the bottom. Our limits are going to be x equal to 0 and x equal to 2. So the area that we're seeking then, the green area, is going to be the integral from 0 to 2, the function that's on the top, minus the function that's on the bottom. So here we add 1 to the exponent and divide by the new exponent. Here it is x to the 0. We add 1 to the exponent and divide by the new exponent. There's the minus sign, and now we have to compute this integral, we have to do a u substitution. I didn't show you the details of the u substitution, but you should be pretty good at that by now. And so what we get by the time we manage our signs, SIG and S's, This is going to be 1/2 e to the minus x squared. I evaluate this at 2 and subtract off this integrand evaluated at 0. When I put 0 in, I get 0, 0, and e to the 0 is 1. When I put 2 in, you do the calculation, and at the end of the problem, your exact answer, found without using a calculator, is 7/2 plus e to the minus 4/2. Some students would say that's an ugly number, but there are no ugly numbers, just like there are no ugly babies. Let's look at another problem. Determine the area of the region enclosed by x equal 1/2 y squared minus 3 and y equal x minus 1. You know what to do and when to do it. Let's see how you did. So the graph of x equal 1/2 y squared minus 3 is a parabola that opens to the right, and this is a line with y-intercept of -1 and slope of 1. There are two ways that we can do this problem, though. If you think about what this green area represents, we could do it as we often have done, and that is it's a limit of Riemann sums, so we could be drawing the slices vertically like this, and we would be integrating dx. But in this problem, we should note that if we're doing that, what happens is here, if I'm doing dx, the function that is on top is this upper branch and the lower branch till you get to this point, this value of x. And then what happens is the rest of the way out, it's going to be this function is on top, and the function that's on the bottom is this one if we're integrating dx. Now we're going to do that in a moment, but a much easier way to do the problem is to integrate this with respect to y. So I'm drawing slices that are horizontal slices. Those are dy, and you notice that the curve for the entire interval that has higher values of x is going to be the blue one, and the other one is going to be underneath. So this is going to be a simpler integral. So we're going to integrate with respect to y first. Now that means what we have to do is we have to solve where are these points of intersection. Actually, we have to do this either way. So the easiest way to do that is to solve this one for x. So x is equal to y plus 1. This one's already solved for x, so x equal x. We set those two things equal, and we solve the quadratic. This one fortunately factors, and so what happens is we know that this is going to be equal to 0 when y is 4 and when y is -2. When y is 4 and when y is -2. I'm going to take the 4 and the -2 and substitute into either one of these equations, and I'll find out that the points of intersection are going to be -1, -2, and the other point of intersection is going to be 5, 4. Those are important. And remember, we were going to now be integrating dy. So the blue function is on top and the red function is underneath. So the blue function is, and again we're integrating dy, so I have to have this looking like y, so I had to solve for x. So this is going to be, I go from, and again it's the y limits, so I'm going from y equal -2 all the way up to y equal 4. This has to be a function of y, so that is going to be y plus 1 minus, and this is going to be the function that's on the bottom, which is this. There's algebra involved in integrating this, and let's do some algebra first. So it's going to be -1/2 y squared. We get that there. This is going to be the y, and here I have 1, and that's minus a -3 makes me 4. So now I'm integrating this. I add 1 to the exponents, divide by the new exponents, and use the fundamental theorem of calculus to evaluate this at 4, and subtract off this evaluated at -2. Quite a bit of calculation to do without a calculator, and we get 18 as the exact answer. Let's do it the other way. Now here, we are again using the x values. We're integrating dx. Remember that we will go from -3 up to -1. This point was, x was -1. So here we have the red is on top and the green is on the bottom. Now we have to solve this though, because now we're integrating dx. That means we have to solve for the y. So if we solve for the y, what we will get is that y is equal to the square root of 2x plus 6 up here, and underneath it is going to be y equal minus the square root of 2x plus 6. So it's going to be the integral from -3 to -1, the function that's on the top, minus the function that's on the bottom, plus, and then we go from -1 all the way to 5. The function that's on top is still the red one, but now the function that's on the bottom is the blue one, and this is going to be x minus 1. We're integrating dx. So now you have two integrals to evaluate. Now here, when you do a minus times a minus, this is going to be 2 times this, and you're going to do a u substitution to do that calculation. And here, you're going to break this into 2 terms. The first one's going to be this one, and then you're going to be integrating this one. You do the u substitutions. You're letting u equal 2x plus 6 on this one and this one. The other integral will be more straightforward. So what we will get is 2/3 u to the 3/2, evaluated at 4, subtracted it, evaluated at 0. We are being mindful of our limits. Notice that the limits changed. Here, you're doing the same thing, and notice that the limits changed. You see this was a u, so your limits have to be u's. This integral is pretty easy. You add 1 to the exponent, divide by the new exponent. Here you add 1 to the exponent, divide by the new exponent, and we calculate this at 5 and minus 1. This is also going to give us 18, and a serious student would go through and actually do that calculation. Here's the last example I think we're going to do in this part. Find the area of the region bounded by this and this. You know what to do and when to do it. Let's see how you did. Okay, so this is the curve that you should have gotten. And you see this would be pretty complicated if you were trying to do this dx, because you see we would be drawing slices like this. So you see the function that is on top here would be the red function on top and the red function on bottom. Then what happens is you have the blue function and the red function, and over here eventually you would get the blue as on top and bottom. It would be a very complicated thing to do dx. Much easier to do dy. So let's solve it. So when is this equal to this? We work through and we solve the quadratic, and we find that that's equal to whenever y goes from -1 to 3. The one that is on top in terms of the value is this one. The one that's on the blue one. The one that's on the bottom is the red one. I have to do some algebraic simplification here. I'll let you check that. But there is going to be the integral of the function on top minus the function on the bottom. When you do the calculation, you simplify it to this, and this is not a bad integral, although there is quite a bit of computation, and you get it as 64 over 3. We've seen this answer several times today, but that's not always going to be the case. That ends part 2. This is to be continued in part 3. See you then.